Now that we've had our fair share of math for a bit, let's go back to some ideas. We talked about the electric field not as a property of individual charges. We don't say the electric field of this charge is blah blah blah. It doesn't make sense to say that. Rather, the electric field is a property of space, so it's appropriate to say the electric field at this point in space is blah blah blah. Much later we'll find the electric field can be a property of time as well, and doesn't have to be a constant vector value in space. What we can say though is the electric field due to this charge at this point in space is blah blah blah. The presence of charges creates electric fields in space, and changing the positions of those charges changes the vector values of the electric field at each of these points in space. Now, if we're interested in the general behavior of the electric field near these point charges, it can be a bit tedious to draw out individual electric field vectors at a bunch of points. Rather than doing that, we can draw electric field lines that are tangent to the electric field at all points in space. Being able to draw electric field lines is a useful skill, but there are some nuances involved, so let's start with something easy. Suppose we had a bunch of electric field vectors pointing in the same direction. It doesn't even matter that they have the same magnitude, just so long as they're in the same direction. The electric field lines for this configuration might look something like this. Each of the field lines is tangent to the electric field vector that's touching it. Now, admittedly, it doesn't take much work to make the electric field lines tangent to these vectors. We just draw them in the same direction as the electric field vectors and we're good to go. The directions of the field vectors never change, so the directions of the field lines don't have to change either. So let's try something else. What about an electric field configuration that might look like this? Now, before the police come after me, I just want to be clear that the configuration you see on the screen here is not possible in real life. We'll see why much later if you're following along with the calculus sections. But suppose it were possible. What might some electric field lines look like due to this field configuration? At every point, the electric field line is tangent to the electric field. As long as the electric field changes smoothly between each point, we're in good shape. Now let's reconsider Coulomb's law in a different light. Consider the electric field lines due to a positively charged particle. Each of the field lines are pointing tangent to the electric field vector at each point, so they create a pattern of radial lines emanating away. An interesting property of electric field lines in the context of point charges is that when the lines are closer together, the electric field is stronger than when they're farther apart. See, when we're close to the charged particle, the field lines are closer together. The electric field is relatively quite strong at this point. As we know, we have the magnitude as inversely proportional to r squared, so if r is small, the magnitude of the field is big. On the other hand, when we're far away from the charge, the electric field is relatively weaker, as the magnitude of the electric field is smaller since r is bigger. The field lines are farther apart, providing a visual illustration of the fact that the field is weaker here. A natural question at this point might be something like, well, that's not really fair. Couldn't you just have drawn more electric field lines? Then there would be more field lines going through this region that's far away. True, but look at what we've done here. Not only are there more field lines farther away from the charge, there are even more electric field lines close to the charge. We haven't changed the fact that the field lines are denser near the charge than away from the charge. While we're on the subject of point charges, why don't we talk about how electric field lines behave with respect to point charges? If you have a positive point charge, field lines travel away from the point charge. This should make sense since, at least near the point charge, the electric field is pointing away from the charge. A small positive test charge would be repelled by this source charge in the middle, so the electric field points in the direction of the electric force that a positive test charge would feel. What about a negative charge? If you have a negative point charge, field lines travel toward the point charge, since the electric field points toward it. A small positive test charge would feel an attractive force toward the negative charge. A small positive test charge would feel an attractive force toward the negative charge, and the direction of the force defines the direction of the electric field vector, which defines the direction of the electric field lines. Another property of electric field lines is that they do not cross, ever. Imagine if electric field lines could cross. What would that mean? Any electric field line we draw is always tangent to the electric field vector at each point. That would mean that the net electric field vector at the crossing point has two different values. But that's not possible. The net electric field vector at each point can only be a single vector value. A point in space can't have more than one associated net electric field. And thus we've proven by contradiction that there's no way for electric field lines to cross one another, since the net electric field at a point in space and time can only be a single value. For the rest of this video, I'll show you some specific cases of electric field line patterns, and we'll try to discuss them. Let's go back to the situation we had earlier with two point charges of opposite sign. We see the electric field lines make this weird spider-looking pattern. They indicate that the electric field is generally pointing away from the positive charge and toward the negative charge. I want to draw your attention to this vertical line that's going down the middle here. This is the only line for which the distance to each of the charges is the same. Well, interestingly enough, the electric field everywhere on this line points straight to the left. I don't know if this is intuitively obvious to you, but it's not obvious to me, and I'm always subconsciously surprised every time I see this horizontal business, especially the vectors far away from the charges. For our next example, let's consider the same scenario, only swap out the negative charge with a positive charge. Such a minor change, so the field lines shouldn't look that different, right?
Wrong.
Here's what the field lines look like. Very interesting. Instead of connecting with each other like the positive and negative ones did, these ones seem to diverge from one another. So what's going on at the midline this time? Now the electric field has a tendency of moving away in the vertical direction from the origin. However, right at the origin, the electric field is zero. The behavior of the electric field roughly in between the two charges is to move toward the center in the horizontal direction and away from the center in the vertical direction. Finally, I want to go over a few examples where we have different magnitudes of charge. Here, the charge on the left has twice the magnitude of the one on the right. We see that the electric field lines are twice as dense near the larger charge. And again, there's some spot in the middle where the field lines meet head-on and the electric field is zero. What if we bump it up to 3 times the magnitude? We end up with kind of a similar story to the previous situation, but just a bit more extreme. In the next video, we'll talk about the simplest of all possible electric field line configurations, the uniform electric field. See you then.